So why did I bore you with this annoying demo that basically shows nothing? That's a very good question. So you notice that this actually resembles our actual work more than just all the demos you see where everything works. Usually, when you do something at the office, you expect it to be simple. You write something, it should take like 5 minutes, but then you got sidetracked and you start doing a lot of stupid debugging about unrelated stuff like Python 2 and Python 3, which you didn't even care about. You only want to use Flask. And then you discover that PYC, which is like, what is that? Like, isn't Python dynamic? What is the PYC anyway? Getting in your way and a lot of yak shaving, basically. And this is actually how we work. Our model of work where you just go and do stuff is completely bogus. And the reason is complexity, basically. So I wrote 5 lines of code, which is supposed to be simple. But actually, if you start thinking about it, what I've actually done, I've orchestrated a Python model. And that Python module has dependencies. So I'm actually using 6 Python modules. So if we count the number of lines of code there, it's about 40,000 lines of code. Of course, that uses CPython and other C libraries like OpenSSL and so on. So it's actually 5 million lines of code. But there is that thing that's called an operating system, Linux in my case, actually OS X. But Linux is additional 30 million lines of code. So it's like 5 lines of code, but dragging on the complexity of about 40 million lines of code. So this is very important to understand. Whenever someone comes to you and say, let's use a microservice, it's going to be so simple, 250 lines of JavaScript. Yeah, right. This is what our universe looks like. And this is an actual representation of Python dependencies on PyPy. And my code, or your code, in that, whatever the case is that tiny dot over there in this huge galaxy. We all live in a complex system. We're surrounded by a lot of modules, a lot of libraries, a lot of services, and we interact with them. And we can't actually achieve anything without using all of that. And it's all complicated. There's a whole big universe around us that we're completely unaware of. So basically, complexity. And complexity grows at an alarming rate. So I'll give you a very interesting statistic. Medical knowledge, for example, doubles every 5 years. Now, how long is medical school here in Israel? 7 years. So by the time you go out of medical school, everything you know is deprecated. Well, not deprecated, because some of it is still relevant. The basics are still relevant. But everyone is ahead of you already. And you've just finished school. Do you continue learning on the job? No, you have to work. Well, of course, you have specialty. Then you have subspecialty. Then we're going to have sub-specialty, maybe sub-sub-sub-sub-specialty. At some point, we're going to be learning for 30 years just to get to the tip of knowledge, of current knowledge, not even advances. It got to a point where no single person today actually understands how things work from top to bottom. If you go on an airplane, if you're an aeronautics engineer, you might understand how the plane flies, but you don't understand the engine. You definitely don't understand the program that's on the autopilot. If you're a programmer, maybe you understand the autopilot, maybe, but you definitely don't understand how the plane flies, and so on. Nobody completely understands the system. This is also true for our systems. I have no idea how the kernel works. It's magic. It's magic. I can open it. I can read the code. Of course I can. But it's a lot of code and a lot of complexity and a lot of domains that I'm not really familiar with. It's going to take me a lot of years to truly understand the kernel. And by that time, I have to deal with databases, web servers, networking, and so on. It's impossible to understand everything. No single person can fit everything inside his head. Cool. So how do we actually get shit done? Basically, we have faith. And without faith, we wouldn't be able to function in this world. We have faith that the ceiling won't fall on our heads. We trust that some civil engineer did the necessary computations and found that this ceiling is strong enough. But we don't know. We haven't checked the numbers. We don't understand enough engineering to verify the numbers. Basically, we believe. We believe everything will be okay. We go on a plane, we believe the plane will not crash, that it will actually get off the ground. We need faith in order to be productive. Basically, we believe in abstractions. That's the way we work. We use abstractions because we can't fit everything inside our head. Now, what is the problem with abstractions? What? Sorry? They don't always work. Yeah, that's very, very true. So, let's give an example. Anybody heard about this? Zookeeper poison packet outside of Adam? No? Oh, another person. Cool. So, Zookeeper poison packet, that was discovered by PagerDuty. I recommend that you read it. It's a very interesting read. Basically, it's 4 different bugs, 2 bugs in Zookeeper, 1 bug in the TCP stack. Basically bypassing checksum checks in the kernel of IPsec packets. And then another bug in the AES encryption model in Linux, but only on Zen Power Virtualization mode, versions 3.1 and 4.3. It's like, what the f? And it interacted between 3 completely separate layers that all were supposed to have like solid abstractions. They were not supposed to be interacting, ever. And then it happened. And this is actually very common, much more common than you would think. If you start looking up on the internet or in postmortems, you would see that that kind of stuff happens all the time. But no single person understands the whole stack. How do you even debug this? Like, would you even look at IPsec or the kernel when you had the Zookeeper bug? Probably not. So it took PagerDuty a very long time to find this bug. They worked on it about over a month, actually. And even after a lot of time they spent researching this whole thing, they still are not actually sure what the hell went wrong there. And this is, again, very common. We don't understand what's going on. The Law of Leaky Abstractions. This was written by Joe Spolsky about like 14 years ago, more or less. If you don't know this, go read it. Really, really cool. Basically, all abstractions, to some degree, are leaky. Everything breaks, and all abstractions will break, and everything will leak up, and we will have to debug this. It's a fact of life. Yes, we need abstractions in order to be productive, but we have to understand that they all leak. At some point, we will have to debug them. But again, no single person understands how the entire system works. How do we even debug this? How do we know that we need to debug this? It's a big problem. So let's take a look at how we work today, currently. So as an engineer, you learn how to code. You code for a few years. You do some stuff. You build some applications. And you learn some architecture and design patterns and all the stuff that they teach you, maybe some TDD. And then you change your job, maybe every 2 years or so, because why not? And then you may be interested in Mongo, so you go to a company that uses Mongo, and then you hear that Node.js is the next best thing, so you go work for this company that uses Node.js. And basically, the average lifespan the average tenure of an engineer currently is about 2 to 3 years in a company or in a job. And we focus on features when we do stuff. We need to roll out stuff, to roll out products and features. We accumulate a lot of technical debt. And we only fix stuff when it breaks. And we only do the minimal amount that we have to do in order to get things to work. And then we continue and we add more features and more features and more features. And when we build systems, basically we just slap on a couple of libraries. Maybe we add a framework because frameworks are cool. And so why not? Why not use Ruby and Rails? And maybe Node.js and React at the same time, because why not? And then we slap on a database. But we need scale because obviously the company is going to have 1 million users next week. So we have to use Cassandra and Mongo, both of them, and Kafka just to get everything connected. And this is how we build stuff. When we ramp on really, really fast because it's all open source and cool, and maybe we get Kafka as a service or Elasticsearch as a service. So it's so easy to add all those components. And then we code. And we test, and we release. And our code is, just tiny amounts of code. 5 lines of code here, 5 lines of code there. Just the glue between all those components. So easy. And our organizations are also structured in a very similar way. We've got management, we've got procedures on documentations to guide everyone, we've got departments. And why do we have departments? Because no single person understands the job. So, we have to kind of contain the job into an area that we can actually fit in our head. And then we've got architects, orchestrating the way departments work with one another and technology is built with one another. Basically, the very Okay, we're back. Last year I was here I was speaking at DevOpsDays about mathematics, and throughout my entire talk, everything stopped working, all the time. The projector, the laptop, everything. At some point I was starting jumping up and down on the floor to make everything work. So apparently it's my destiny to break stuff. Anyway, so basically the interesting observation that I've seen anyway in the organizations is that we have teams on the bottom, but as you move up in the hierarchy of our organizations, you actually see that you have individuals on top. You almost don't see teamwork on top. You've got a team of developers, but you don't have a team of CEO, do you? You've got one CEO, one chief architect, and so on. Very interesting. Basically, we're building everything assuming that we live in a predictable world, in a world that we can understand. And this is the reason why we've designed our organizations and our systems in such a way. The reason why we have individuals at the top is because we're assuming one single person can actually understand all the relevant context. And this is not the case. Software development is a learning process. We don't understand the world. We don't understand the problem. We don't understand the environment. We don't understand our clients. And when we're building software, we're basically learning. We're learning the environment, we're learning the system, we're learning new technologies all the time. We're researching our own system because sometimes we don't even understand the system that we've built. If you spend 6 years building a system, it's going to be complex to the point where you don't actually understand the system, and you will have to research and learn that system when you add new features. So this is very, very important to understand. And once you understand that software development is a learning process, you start rethinking how we work and how we construct our organizations. Software development is not a sprint. Contrary to what agile methodologists would, or I should say acolytes would tell you, it's not a sprint, it's a marathon. It takes a very, very long time to get anything done, especially if it's big and complicated and, worthwhile. The Sistine Chapel, for example, this particular painting took 4 years to paint. Michelangelo spent 2 years on his back painting this, and he had 16 helpers helping him with this picture. The whole of the Sistine Chapel took about 12 years to complete. It takes a long time. Learning takes a very, very long time. And it's not only the accumulation of knowledge. At some point, knowledge consolidates, and you start getting intuition. You start understanding things. You start ramping up your knowledge. This takes years. For physics students or chemistry students, it takes about 2 to 3 years just to, to start to actually consolidate knowledge and transition from a state where, you've got a bunch of unrelated courses to actually understanding physics. It's the same for everything that we do and everything that we learn. In software, it takes, again, 2 to 3 years just to start to understand the mechanics of software and transition from a state where you have a bunch of algorithms and a bunch of languages that you know and actually have knowledge. Expertise takes a very, very long time. MySQL and Postgres have been developed for over 20 years. MySQL for 21 years, Postgres for 20 years, and they're not done yet. They're still very much alive and very much in development. And why is that? Because it's an evolution. MySQL and Postgres have evolved. The clients have co-evolved with Postgres and with MySQL. The databases have learned more about the universe, about the needs of the clients, about the environment, the operating environment that also kept changing and evolving. The clients, the people who build applications, they also learned about the way Postgres is doing stuff, the way MySQL is doing stuff, about how databases behave. They also evolved. This is a process of very, very slow evolution, of co-evolution actually. And it takes time. And we have to go through this process in order to get something that works and works well. Boils down to maturity. But how can we have maturity if we change framework every time new JavaScript framework comes along, which is basically every 2 weeks? How can we have maturity when we're changing jobs every 2 years? Again, learning takes a very, very long time. Expertise takes a long time. Expertise takes about 20 years to develop. 20 years. Is there anyone in this room who's been at the same job, or at the same domain for 20 years? Anyone? 1, 2 people. That's it. So we have 2 experts in this room. That's it. So we need better coping mechanisms for a complicated world. You should go talk to Corey Quinn about this. He knows a lot about coping mechanisms for DevOps. Yeah, go talk to him after this. So we all have R&D departments. Here's a question. I've observed people in R&D departments doing development, but where's the research? What research are they doing in R&D? So often you would go to a company and you would ask, so where's the research? And they would point to a different department called research department full of people doing algorithms. Okay, but then you have the R&D department, which is not doing research. So what exactly are they doing? Well, they are in R&D. So what kind of research should we have in R&D? We need research into our own systems, and we need to research development methodologies and development processes, and we need to research the operating environment that we live in, because it's complicated and it keeps changing all the time. So the kind of organizations that we want to build are learning organizations, organizations that are built around the concept of learning and research. First of all, we need to understand that engineers need different skills. Debugging is a very, very important skill for a complicated and complex world, because if you don't understand the world, you need to debug it, and you need to be able to learn and slice and dice it and be able to extract new knowledge from that world. This is a very, very rare skill with engineers. A lot of engineers don't know how to debug. Nobody ever required this from them. And sometimes they were actually discouraged from debugging. Maybe someone didn't give them root to the machine, so they couldn't debug. We need system thinking. Understanding how everything fits together, not just your local tiny part. Because again, 5 lines of code, right? We need research methodologies. I was lucky to learn at university some research methodologies. A lot of people were not that lucky. They don't know how to research. They don't know how to construct a working theory or conduct an experiment, which is, again, very important for solid learning. And of course, we need teamwork, because no single person understands the system. We need a team of people to understand the system. We need to build a body of knowledge, experts, domain experts. And we need those domain experts. I don't think Wix could function if we didn't have people that were there for 6, 7 years and basically know the history of the system, know how everything fits together, and what would break if we change this, and what will be pulled apart if we change this here, maybe something on the opposite side of the system. And we have those people. We have people that have been in Wix for that long and know the ins and outs of the entire system, and it would be very, very hard to function without those people. So we need people that have a very long tenure. In every company, every successful company at least, you would find some people that have been in that company for a very, very long time. But you also need to give those people the resources and time to develop. They need time for research, time for learning. Raise your hand if you've read an academic paper about software development in the last year. Okay, that's about a fourth of the room. You should all be reading academic papers, and not just once a year. Okay, sorry, about reading. Who read an academic paper in the last year? That's, again, about a third of the room. And so it's interesting to see that it's the same amount of people reading and writing. So, yeah, we should all be reading academic papers constantly. This is learning. We need to understand how things work. We also need system thinkers. We need people who know everything horizontally, but not necessarily deep. People who are expert in integration and debugging and how things work together. How are we going to get those people? We need people that move between technologies, but not necessarily between systems. People who are experts at systems. We all have them. Sometimes we call them operations, problem solvers, and so on. But they're very, very important because in a complex world where everything connects together, you cannot debug anything if you don't have someone who knows how things connect and how things work in unison. And they're also experts at learning because their job is constantly getting into new systems that they don't know and ramping up knowledge at a very fast rate. We need to design with complexity in mind. Just slapping on a couple of libraries without regard to complexity is horrible. This is how we got to the sorry situation that we don't understand the system. We should try to religiously simplify the system if it's possible. Often, it's not possible to simplify the system. In this case, we should realize that understandability and debuggability and visibility are prime concerns for the system. We should be designing for understandability. If you can't fit the design of the system in your head, there's no chance you will ever be able to debug it and find problems, or even predict what the system will do. Okay? This is not the case, unfortunately. Often when people select a library, they don't even check if that library is debuggable. Maybe it doesn't even emit metrics. Maybe it's written in such a way that it's impossible to debug. This is not even a decision criteria for most people. So again, this should be a primary focus when we design systems. And finally, we should learn the value of maturity. Mongo is now better, but a few years back, everyone was like, Mongo is web scale. You should use Mongo. It was like 1 year old. What are you kidding me? Database maturity takes about 15 years to become mature. 15 years, okay? We should learn the value of maturity. And especially when we're talking about infrastructure, because everything is built on top of infrastructure. Infrastructure needs to be predictable and understandable. And experience with technology is very, very valuable. This is how we gain faith. This is how we get to the situation where we can actually believe in how the abstraction works, because we have experience with it. We know the quirks of the system. We know where to look when something breaks. We know how to debug it. Operating experience is probably one of the most undervalued qualities in software development, unfortunately. We need to prefer momentum over velocity. So every time I go to a software engineering conference, people just speak about velocity, velocity, velocity. We should have velocity in development, blah, blah, blah. We should have momentum. And momentum comes from solid infrastructure. And momentum takes a lot of time to build. Again, this is a marathon, not a sprint. You should probably look into the case of slow programming. Really cool. And if we want to do research, we need to give it time. We need time to experiment. We need time to do research, time to build simulations, time to build toys that we can learn from. Often people focus on features, and we don't have the time for that. Complexity is here to stay. There's no way around this. The systems of the future are going to be more complicated than the systems we have today. There's no way around this. We need to understand how to build organizations, and how to train engineers that can deal with complexity. So thank you very much.